In this lecture, I'm going to talk about Langmuir adsorption isotherm. First, let me explain postulates of Langmuir adsorption isotherm. He assumed the following points. Langmuir actually assumes the following points. That is, there is only a single layer is formed. There is only a single layer is formed. That if you have a solid surface, you have a solid adsorbent. Only he assumes that there is formation of only single layer. And the another point that he visualized the adsorption as like this, that there is a condensation and evaporation takes place. According to him, this is a solid, this is the adsorbent. You see the molecules actually condense on the surface, and the condense on the surface, I mean they are adsorbed. At the same time, the molecule will desorb. The already adsorbed molecule will desorb or will be evaporated. This is another point that he assumed. So condensation and the evaporations, both the process actually two opposing process actually takes place. This is another another assumption. So he assumed that adsorption actually forms only the monolayer, and he assumed that the condensation and evaporation actually takes place. Both the condensation and the evaporation actually takes place. Condensation, it is actually adsorption. It is condensation is actually adsorption. Evaporation, it is desorption, that the molecule already adsorbed will move away from the surface. This may be due to thermal agitations. He postulated that this is maybe desorptions may be due to thermal agitation. The another important point is that the adsorption rate initially will be more, because if you see here, this is the adsorbent. Initially the adsorption rate will be more, because you see large surface area is unoccupied. It is directly proportional, the rate of adsorption is directly proportional to the unoccupied surface area. So you see at beginning large area is available for the adsorptions. Therefore at the beginning the adsorption rate will be more, but after some time adsorption will take place, and it covers all the surface area. Then you'll have the solid will have very less surface area. So the rate will falls down when the molecule occupies all the surfaces. Then the rate of adsorption actually decreases. This is another important postulates that he made. Next another postulates is that the adsorbed gas or not, they do not move around. They simply, this is the adsorbed gas. This adsorbed molecule or adsorbed gas, they will not move around. They will simply localized in that particular area. This molecule will not just randomly move here and there. They are just localized in that point itself. They will not just move. That's all. And then no interactions will be there between these two adjacent molecules. That means lateral interactions will not be there. This is another point that he assumed. And so based on all these assumptions, he actually derives an equation. So I'm going to derive the equation. Before that the rate of adsorption and the rate of desorption. The rate of adsorption is actually directly proportional to fraction of surface area not covered. I just need to give you an explanations about this. adsorption, the rate at which the adsorption takes place depends on the fraction of area not covered. As I said already, the desorption is actually takes place the fraction of area that is covered. You know, if the surface, if you have large surface, the rate of adsorption will be more. That means the adsorption is directly proportional to the surface area which is not covered, the fraction of surface area which is not covered by the adsorbent. So that is directly proportional. Adsorption will be directly proportional to the fraction of surface area that is not covered. But desorption, that is the evaporation, that is directly proportional to the fraction of surface area covered. If large fractions of surface area is covered, the large number of molecules are available to undergo desorption. Therefore, desorption process directly proportional to the fraction of surface area that is covered. Here, theta is the surface area. Theta is a fraction of area. Theta is the fraction of total surface area covered, and 1 minus theta will be total surface area which is not covered. Then what is theta? It is a fraction of surface area that is covered, that is occupied. Fraction of this is the total surface area. It is now free. When molecules occupies, say, let me assume some 1000 centimeter square is the total surface area available, and if you consider some 600 centimeter square is occupied, then this fraction is called this fraction is called 0.6, right? This fraction is called theta. This much of 0.6 fraction, 0.6, this much of fraction is occupied. This much of surface area is occupied. That is actually theta. Theta is a fraction of total surface area covered. But uncovered surface area will be, okay, this is 0.6. Okay, the uncovered surface area will be 1 minus theta, because if you have 1000 centimeter square total surface area, if all the 1000 centimeter squares will be occupied, then the fractions will be 1. So the maximum fractions will be 1. Therefore, the unoccupied will be, this is occupied, theta is occupied, the surface area which is the fraction of surface area which is occupied or covered is theta. The unoccupied will be 1 minus theta. 1 is actually, it's a, that will be the maximum value, because it is said in terms of fractions. Okay, with this with these points, let me derive the Langmuir adsorption isotherm. The rate of adsorption is equal to the rate of adsorption or you can say it is rate of condensation. The rate of condensation is the rate of condensation. What do you mean by that? The rate of adsorption is directly proportional to surface area unoccupied surface area. Unoccupied surface area is 1 minus theta. And also the rate of adsorption or the rate of condensation depends on the pressure. That means if you have this container, then this is your adsorbent. If higher is the pressure of the molecule, then the rate of adsorption will be more. So the rate of adsorption is also directly proportional to the pressure, equilibrium pressure of the gas. So let it be the equilibrium pressure. P is the equilibrium pressure, and I'm here introducing a constant, proportionality constant. And evaporation, the rate of evaporation, is actually directly proportional to, what do you mean by rate of evaporation? Just explain. Rate of evaporation is, or desorption, evaporation or desorption. The rate of evaporation is directly proportional to fraction of surface area covered. What is fraction of surface area covered? Theta is the fraction of total surface area covered. Theta is the total fraction of area, surface area covered. Therefore, the rate of evaporation is directly proportional to theta. I'm introducing here the proportionality constant. So, desorption and the rate of adsorption, and at the rate of desorption, or the rate of condensation on the rate of evaporation, they will be equal when equilibrium is established. So we previously learned that equilibrium is actually established. Equilibrium is actually established between here adsorbed and this is the adsorbed molecule, and the molecule which is near, there will be equilibrium. So there will be equilibrium between adsorption and condensation. There will be equilibrium between adsorption and condensation. So this is called adsorption equilibrium. So at adsorption equilibrium, the rate of evaporation, the rate of adsorption, and the rate of desorption will be equal. This is rate of adsorption, and the rate of desorption or evaporation will be equal at equilibrium. Okay, let me now simplify this equation to get theta. So therefore theta equal to K1P divided by K1P plus K2. Okay, now now just I'm going to divide numerator and the denominator by K2. Therefore theta equal to K1 by K2 into P divided by K1P plus K2 by K2. One. Now I'm just K1 by, I assume that I K1 by K2, K1, K2 they are constant. Therefore I introduce another constant, a new constant. I'm just substituting B for K1 by K2. Therefore this equation becomes simplified. B plus Bp plus 1. Therefore theta equal to theta equal to BP by 1 plus BP, right? So theta is actually fraction of area that is covered, fraction of area, surface area that is covered is theta. And so B is actually K1 by K2. Now I know Y is directly proportional to theta. Y is called the amount of gas absorbed. Y is called the amount of gas absorbed per unit mass of adsorbent. That is Y. So Y is actually proportional to the amount of absorbed area. The amount of absorbed gas, the amount of absorbate is directly proportional to, of course, a fraction of area covered. That's what this is adsorption isotherm. We actually plot Y versus pressure. Y is actually the amount of adsorbed material, and this amount of adsorbed material Y is actually directly proportional to fraction of area covered. If large area is covered, if large area of the surface is covered, then Y value will be more. So the Y value depends on the fraction of area covered. So therefore Y is directly proportional to theta. Let me introduce the proportionality constant K and P. K and theta. I know theta is derived, the expression for theta is derived here. Therefore Y equal to K into BP divided by 1 plus BP. And K is constant and B is constant. I'm just substituting A for K and B. So AP divided by 1 plus B. This is Y is actually the amount of adsorbed material. Y is the amount of adsorbed material. The constant A is actually K into B. Sorry, B. Okay, then this equation, that is the amount of adsorbed material, is equal to AP is a constant, 1 plus B is also a constant B. This equation is called Langmuir adsorption isotherm. This is called Langmuir adsorption isotherm. Right. So now I'm going to check validity of this equation. What I'm going to do is I'm going to divide this equation by P, pressure, for AP by 1 plus BP divided by P. This is AP divided by 1 plus BP into P. So the P cancel. A by 1 plus BP. This is Y by P. I am going to invert. I am going to take a reciprocal of this equation. P by Y equal to, I'm just going to take a reciprocal of this equation. This is 1 by A plus BP by A. This is P by Y. Now this is, A and B, they are constant. A and B are constant. Now this is in straight line format. This is y-axis. Slope is B by A is slope, and pressure mx plus C. Okay, if I plot pressure in the x-axis, and if I plot pressure in the x-axis and P pressure but divided by the amount of adsorbed material, P by Y in the x and the y-axis, I must get a straight line. I just perform adsorption experiment and find out at various pressure the amount of adsorbed material. If I plot y-axis in the y-axis P by Y and in the x-axis pressure, if I get a straight line with a positive slope like this, then this equation, this is acceptable. This Langmuir adsorption isotherm is acceptable. If I get this, if I get a straight line, if I plot P by Y by versus P, actually this happens. Actually, it gives the experimental value. The experimental value is plotted. You get a straight line. At any pressure. It is not like Freundlich adsorption isotherm. Freundlich gives straight line only at low pressure, but Langmuir actually gives straight line at all the pressure, at any pressure, whether it is low or whether it is high. Therefore, this Langmuir adsorption isotherm is actually valid and acceptable. And now let me take this equation, theta equal to BP by 1 plus BP. This is fraction of area covered. This is fraction of area covered. Let me say at low pressure, let me assume at low pressure, pressure P, the value BP compared to 1 is very less. So therefore I omit BP in the denominator. Therefore theta equal to BP. At high pressure, you see theta is directly proportional to pressure at low pressure. Theta is directly proportional to pressure when at low pressure. And at high pressure, BP is greater than 1. Therefore, I omit 1 in the numerator, in the numerator of this, in this equation. Therefore, theta equal to BP divided by BP. I omit this 1 because its value is very less compared to pressure BP, because the condition is high pressure. Therefore theta equal to 1. So theta that means fraction of area covered. That means the fraction of area covered is actually constant. It is not changing. Therefore, let me put them in plot theta versus pressure. At low pressure, theta is directly proportional to pressure. So when pressure is increased, theta will be increased. So I must get a curve like this. because it is increasing. Then at high pressure, when it reaches high pressure, what happens? P theta is equal to 1. That is constant. The theta is constant. Theta is not changing. So I'll get a curve like this. So I can say this is, in kinetics view, this is first order, this is zero order. So therefore Langmuir, so this looks like, you see y, I said y directly proportional to theta, y directly proportional to theta. You see this curve looks like type 1 adsorption isotherm. This curve actually looks like type 1 adsorption isotherm. So therefore Langmuir adsorption isotherm clearly explains the experimental observation of chemical adsorption. Chemical adsorption actually involves the monolayer formation. I mean, this Langmuir adsorption isotherm explains the type 1 adsorption isotherm. It clearly explains. So this Langmuir adsorption isotherm is superior than the Freundlich adsorption isotherm in explaining this type 1 curve. Then what about type 2 to type 5? These curves are not explained by the Langmuir, and also it is not explained by the Freundlich. So we need another theory to explain all other curves, all other adsorption curves. The another theory is called BET theory. I'll explain it this in next class.